started.
Okay.
All right. Hi, my name is Allison, and this is my audience member, Erin. She's my little sister.
Hi.
And today, for my second presentation about modern algebra, we'll be talking about rings specifically. So first, we're going to go back over what a group is. We covered it in class. We covered it in my first presentation, Erin, if you remember. And we're going to cover it one more time this time. So this is the notation here on the screen. It's going to be parentheses G and a star, G being the set G, and then star being the binary operation that is over G. So in order for something to be considered a group like this, it has to follow 4 axioms. And those 4 axioms are closure, identity element, associativity, and inverse element. So to start off, we have closure, and that's just for any 2 elements in G. If you take them and perform the binary operation, it creates a third element in G, such as 2 integers added together create a third integer. And the second one we have is the identity element. So that's going to be a single element in G, the set G, such that for every element in G, when you apply the identity element to it through the binary operation, you get that same element. So 1 plus 0 is 1, 2 plus 0 is 2, so 0 would be the identity element. All right, and the third one is going to be associativity. So that just says for all A, B, and C, for any 3 elements in G, it is true that you can either multiply the first set first or the second set first. So that's A times B times C or A times B times C. That makes sense?
Mm-hmm.
Okay, so it doesn't matter in which order you perform the operation as long as you perform them on the same 3 elements. So the final axiom is going to be the inverse element, and that just states that for every element in G, there is a unique element also in G such that those 2 elements multiplied together gives you the identity. So what we already established was that 0 was the identity for integers under addition. And if you take a 1, the integer 1, and the integer -1, and you add them together, you get the identity 0. So that makes 1 and -1 inverses of each other. So you have to follow those 4 axioms in order to be considered a group. So now we're going to go over a special type of group, and it's going to be an abelian group. So in order to be an abelian group, you have to satisfy all 4 of those axioms that we discussed before on this slide: closure, identity element, associativity, and inverse element. And then on top of that, you have to follow a commutativity axiom. And that's just going to be that for any 2 elements in the set G again, it doesn't matter which order you perform them in the binary operation, you will still get the same result. That's commutativity. And so just to go over an example of an abelian group, we have the integers under addition, which is what we've been using this whole time. So again, it's closed because any 2 integers added together make an integer. It has an identity element, which we established was 0. 1 plus 0 is 1. 2 plus 0 is 2, so on. We established it's associative, so it doesn't matter which order you add 3 integers in, as long as you're performing the binary operations on the same 3 integers, you get the same result. The inverse element for integers under addition is going to be the negative counterpart of that integer. So 1 and -1 are inverses, 2 and -2, and so on. And then finally, we know that it's commutative because any 2 integers may be added in either order to get the same result. So we know 1 plus 2 is 3, but also 2 plus 1 is 3. So you can add them in either order. That makes it commutative. So now that it covers all 5 of these axioms, it becomes an abelian group. Another type of group that we're going to cover is going to be a monoid. So all groups are monoids, but not all monoids are groups. That's going to be an important factor when we're defining rings. So in order to be a monoid, you have to satisfy only 3 of these previous axioms. So the 3 axioms that you have to satisfy are closure, identity element, and associativity. It does not have to have an inverse. Sometimes monoids may be commutative, but that does not make it a complete group because it still does not have an inverse. So we're going to go over an example here. It's going to be the natural numbers under multiplication with this notation. So it does have 3 of the satisfied axioms. It is closed, associative, and identity, and it has an identity element. So it's going to be closed because any 2 natural numbers, 1, 2, 3, or 4, so on, if you multiply 2 of them together, you always get a natural number. So it's closed. The next axiom is associative. So for any natural number, a times b times c is equal to a times b times c. So 1 times 2 times 3 is equal to 1 times 2 times 3. They both equal 6. And the third axiom is going to be identity. If you multiply any number by 1, you get that number itself, which means 1 is the identity element for natural numbers under multiplication. So that makes it a monoid. However, there's one more thing to note here. It is also commutative. So if you have the natural numbers under multiplication, that makes it something called a commutative monoid. However, it is still not considered a group at this point because it does not have an inverse element. So now that we've covered groups and abelian groups and monoids, we're going to get into what a ring is. So a ring has this set of notation. So for the ring G for the set G under addition and multiplication, it needs to satisfy 3 axioms in order to be considered a ring. The first one is going to be that G under addition has to be an abelian group. So the group G under addition has to be abelian, which means it has to be, again, it has to be closed, associative, commutative, and have both identity and inverse elements. The second axiom is G has to be a monoid under multiplication, which again means under multiplication, the set G has to be closed, associative, and it has to have identity elements. It may be commutative, it may not be commutative. That doesn't change the fact that it is indeed a monoid. The third axiom is multiplication has to be distributive with respect to addition. And so that just means that it has to be both left and right distributive. The top example here, a times b plus c, is going to be left distributive. So that just means it has to be equal to a times b plus a times c. And the bottom here, b plus c times a, is right distributive. And that just means it has to be b times a plus c times a. And both of those answers have to be equal. Both of these, it has to be both left distributive and right distributive in order to be considered distributive under multiplication with respect to addition. So if it follows all 3 of these axioms, it is considered a ring. So we're just going to run through some examples real fast so that you can get the hang of it, Erin, so that you can get the hang of it too, because then we'll be running through some exercises. Okay. So the first example is integers under addition with multiplication. So integers represented by z and then addition and multiplication. So we know that it is an abelian group under addition because it is closed. As we already went over in the previous slides, it is closed, associative, commutative, and it has both an inverse, which is going to be the negative counterpart of any number, and it has an identity, which is going to be 0. And then the second axiom, z has to be a monoid under multiplication, which we do know it is, because if you multiply any integer with another integer, you're always going to get an integer, which means it's closed. You can multiply 3 integers, performing the binary operations in any order, which means it is associative. And it has an identity element, because if you multiply any integer by 1, you get that same integer. Right. We also know for the third axiom that multiplication is distributive with respect to addition over the integers, because we know 1 times 2 plus 3 is equal to 1 times 2 plus 1 times 3. So because it covers all 3 of these axioms, the integers under addition and multiplication is going to be considered a ring. Our second example is going to be 2 by 2 matrices with real numbers under addition and multiplication. And that's going to be using this notation right here, m subscript 2 of R, which just means 2 by 2 matrices with real numbers. So the first axiom means that it has to be an abelian group under addition, which means it is closed. We know it is closed, associative, commutative, and it has both an inverse, which is going to be the negative counterpart to any matrice, and we know that it has an identity, which is going to be the zero matrice. So it is an abelian group under addition. The second axiom is going to be a 2 by 2 matrices with real numbers under multiplication. It has to be a monoid. We know that for monoids, it has to be closed, associative, and have an identity, which it is closed and associative, and we know that the identity element for 2 by 2 matrices with real numbers is going to be the identity matrix. So it is a monoid under multiplication. The final axiom is multiplication has to be distributive with respect to addition over 2 by 2 matrices with real numbers, and we do know that you can distribute matrices over addition with multiplication. So that makes this entire 2 by 2 matrices with real numbers under addition and multiplication a ring. So now we're going to move on to some exercises. So first we're going to be looking at, is the set of integer modulo 4 a ring? So it's going to be using this notation, z subscript 4, and then it's going to be comprised of the set 0, 1, 2, 3, and it's going to be a cyclical set. So, and we're looking at it under addition and multiplication. So the first axiom is going to be, it has to be an abelian group under addition. So first we want to find out, is it closed? If we add two of these numbers, does it create a third number in the set?
Yes.
Yes, it does. So it is closed. The next question is it associative? So if we add 3 of these numbers, adding the first pair and then the second pair, is it the same as adding the second pair and then the first pair?
Yes.
It is, yes. So if we added 0, 1, and 2, 0 and 1 make 1, 1 and 2 make 3. But let's say we added 1, 2, and then added 0, 1 and 2 make 3, plus 0 is also 3, they're the same. So yes, it is associative. Now we're going to look at if it has an identity element. So is there an element here where if you add it to any other element, you get that same element?
Yes.
So the identity here is going to be 0. If you add any number to 0 in this set, you're going to get that same number. So 0 plus 3 is 3, 0 plus 2 is 2, so on. So yes, it does have an identity. Does it have an inverse? Does each number have a number here in the set that takes it to the identity element of 0?
Yes.
Yes. This one's a little more complicated, and we walked through it beforehand, so that was good. So if you add, let's take 1 for example. And since this is a cyclical set, we just have to find the number of steps it takes to get back to 0 in order to find its inverse. So 1 to 2 is 1 step, 2 to 3 is another step, and 3 back to 0 is another step. That was 3 steps. So the inverse of 1 is 3. So if you add 1 and 3 together, you get 0. And each of those numbers in the set has an inverse like that. So yes, it does have inverses. The next question we're going to ask is it commutative? If you can take two numbers and flip them around, is it the same result?
Yes.
So yes. So if you add 1 and 2, it becomes 3. If you add 2 and 1, it becomes 3 again. So it's commutative. So since it follows all 5 of these axioms for an abelian group, it is an abelian group. So that is the first axiom of becoming a ring. All right. So the next axiom is that it has to be a monoid under multiplication. So in order to be a monoid, you have to be closed, associative, and have an identity element. So is it closed under multiplication? If you multiply 2 numbers of the set, do you get another number of the set?
Yes.
Yes. So let's say you multiplied 2 plus 3, you would get 6, and then modulo by 4, that becomes 2. 2 is still in the set, so it is closed. Is it associative? So if you add 3 numbers together, and you add the first pair and then the second pair, is it the same as adding the second pair and then the first pair?
Yes.
So let's say you wanted to multiply 1, 2, and 3. If I multiply 1 and 2 first, it's the same as multiplying 2 and 3 first. So it is associative. And now it also has to have an identity element. So is there an element in the set that if you multiply it by that identity, you get the same element?
Yes.
And it's going to be 1. It's going to be 1. If you multiply any number in the set, you get that number. So 1 times 2 is 2. 1 times 3 is 3. 0 times 1 is 0.
That's why I said 0.
No.
What?
It's 1. So you have to multiply it by 1 and still get that same number.
But if you multiply it by 0,
you still get 0. Yeah, that makes it the identity.
That's what I was saying.
No. It makes 1 the identity. We'll cover this later.
What if you did 0 times 2?
If you did 0 times 2, you get 0. So you're supposed to get 2 in order to make it the identity. So that's why 1 is the identity. So we know now that it is closed, associative, and has an identity under multiplication. So that makes Z subscript 4 under multiplication a monoid, which is the second axiom for becoming a ring. So the third axiom is going to be Z4 under multiplication. Is it distributive with respect to addition? And we do know that because these are integers, they will be distributing over addition. So it is true. So because all of these axioms are true, it's an abelian group under addition, it's a monoid under multiplication, and multiplication is distributive with respect to addition, that this is in fact a ring. Okay. So now we have another exercise. There it is. It's going to be a simpler one. So it's just going to be the set of element 0 under multiplication and addition. So this is going to be the notation for it here. And again, G is just the set of 0. So is an abelian group, is it closed? Well, yes, under addition, because you're just adding 0 to itself, which is 0. Is it associative? Yes, it doesn't matter which order you perform the binary operation in, it's always going to create 0. Does it have an identity?
Yes.
Yes. That is going to be the only element, 0. And does 0 have an inverse in this set?
Yes.
Yes, it is itself, 0. Is it commutative? Can you add 0 plus 0 and be the same as 0 plus 0?
Yeah.
Yes, 0. So now we know it's an abelian group. So now we need to know, is G a monoid under multiplication? Is it closed under multiplication?
Yes. Yes.
Yeah. And that's just because 0 times 0 is still a set. It is 0. Is it associative? Does it matter what order you perform the binary operations in?
No, it doesn't matter.
It's all going to be 0. Does it have an identity for multiplication?
Yes.
Yes, it is going to be 0. So because of these 3 factors, G is a monoid under multiplication. And the final axiom is multiplication over G distributive with respect to addition. And that's just, can you say 0 times 0 plus 0 is the same as 0 times 0 plus 0 times 0?
Yeah.
Yeah, it's all 0. So this is in fact the set of 0 under multiplication and addition is considered a ring. All right, and then here's some take-home exercises that you can work on yourself. It's the set of all positive integers, Z plus, do they form a ring under addition and multiplication? And then is the set of all integers divisible by 3 a ring under addition and multiplication? So next lecture, I will be branching this out to connect to a magic trick, and this will likely also be posted on YouTube. So thank you for watching, and Erin, thank you for being my audience member.
You're welcome.